Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to wrap up our conversation on electrochemistry by talking about corrosion. So this is simply going to be the process at which we can use redox reactions to destroy things we don't want to. So this is an important thing to note, and especially when working with metals, one of the biggest ways that metallic surfaces can break down is through the corrosion of these metal surfaces, so eroding them through oxidation. So one of the things we can imagine is, say, if I've got an iron surface. Well, it turns out if there's something that can oxidize these systems, as in steal their electrons, then they can go ahead and form either an iron 2 or iron 3 ions. Well, note that what we've done is we've removed material from a solid surface. And so this means that they'll slowly erode and you'll have less and less of your metal surface there. And this is one of the fundamental parts of corrosion. Occasionally, you'll often have things like oxides reform in the place where the original metal used to be. So things like iron, copper, or nickel oxides will often form on top of an eroded surface. But one of the big things with trying to prevent corrosion is trying to prevent the oxidation of these various substances. And it's worth noting that oxidation really can occur whenever these metals are going to be placed in water, because note that you will have to have water present to dissolve the ions that are produced. No water, no dissolved ions, no oxidation. And you'll need a sufficiently powerful oxidizing agent, somebody who wants those electrons enough that they can steal them from your metal, again, forming those ionic species. So, in trying to evaluate the likelihood of oxidation occurring, it's very important to look at our various reduction potentials. So the reduction potential essentially says how much each of these individual ionic species would want to form the solid. The lower the reduction potential, the less likely it wants to form. And so the lower the number, the lower the reduction potential, the more likely that metal is to oxidize. So for example, zinc is going to be very readily oxidized. And copper is unlikely to be oxidized. And pretty much as long as there's a material with a higher reduction potential present, you can end up driving the oxidation reaction of the lower reduction potential material. So for example, if you've got iron 2 or iron 3 plus present, they can go ahead and couple with the zinc reaction to oxidize zinc and forming the zinc 2 plus ions. And conversely, the lower the reduction potential, again, as shown with zinc, zinc is very likely to oxidize, and the least likely to oxidize of all these metals is going to be copper. It is comparatively fairly stable. So what sort of reduction reactions could end up stealing these electrons and driving the corrosion of metals? Well, it's called oxidation for a reason. One of the most common oxidizing agents is going to be oxygen. So oxygen has a fairly high reduction potential of 1.23 volts, as we've seen before. And it can go ahead and accept 4 electrons, which means if I go ahead and combine it with something like iron, so iron, its lowest reduction potential, so the one most likely to oxidize, will be taking iron to iron 2 plus. So with a reduction potential of negative 0.44, it means that iron readily oxidizes to iron 2 plus, oxygen readily reduces to form water. So if we go ahead and combine these into a balanced reaction, we can combine oxygen with some iron to form our iron ions, water. But do note that this process does essentially acknowledge the presence of acidic conditions. So you need to have 4 protons to help drive this formation of the water molecules. So this has an overall potential of 1.67 volts, meaning this reaction is very favorable. So iron is readily oxidized by oxygen. Again, assuming that there's enough oxygen present, and again, enough proton concentration. So as long as I have enough protons and oxygens, we'll be staying fairly close to this standard state potential, indicating that iron will readily corrode to form our iron ions. Again, removing the iron from the surface. So how can we go ahead and remedy this? Well, one of the opportunities we can do is take a look at my list of metals and organize them based on reduction potentials. And we'll note that copper is unlikely to be oxidized. Zinc is very readily oxidized. So what I could do is, let's say I've got something like iron and I want to prevent its oxidation. I can go ahead and find some substance with a lower reduction potential, something like zinc. So zinc is readily oxidized and it's fairly easy to mine and find. So if I go ahead and have zinc and iron both present in solution, all that oxygen comes in would say, why do I want to hang out with iron? Zinc is way easier to mug. So it steals the electrons from zinc and leaves the iron relatively untouched. And it is worth noting there's often other substances you can use, such as sodium or magnesium, but they're a little bit too reactive and aren't quite as stable to environmental conditions. So zinc is the most commonly used. And using such a substance to essentially sacrifice is called a sacrificial anode. As the whole point of adding zinc to the system is that we expect zinc to be destroyed in the place of something else. So we are sacrificing it to save our more valuable iron or copper. And again, there are other possible choices for sacrificial anodes, but zinc, due to its stability and abundance, is a very common choice. So you may say, why on earth would I care about using a sacrificial anode, and when will it impact my everyday life? Well, I bet most of you have heard of something called galvanized iron or galvanized steel. So this is simply a form of iron or steel that's a little bit more resistant to corrosion because you applied zinc to its surface. And the whole idea here is that when I have oxygen come into water and tries to react with the iron, well, it will go ahead and steal electrons from the iron, but the iron says, hey, I want my electrons. Zinc, you don't want your electrons that much. I'm going to steal my electrons from you. So instead of the iron end up producing iron 2+, instead I will corrode the zinc and it will form zinc 2+. So even if oxidation occurs at the iron surface, you're still going to steal the electrons from your sacrificial anode. And this will occur essentially as long as there's a connection in between your zinc surface and your iron surface. And this is used in any number of applications, from essentially preventing your nails from rusting to helping maintain the structural integrity of ships, where there's usually some sort of reservoir of zinc or magnesium or aluminum inside the ship to prevent the iron on the outside from corroding, and instead you slowly erode the less valuable metal, which is in a safe location. So this brings us to the end of electrochemistry. Next time, we're going to try and focus a little bit more on what reactions can happen to what reactions will happen and how quickly will they occur. Until then, take care.